Okay, good morning, everyone. We're in the quantum machine learning seminar in Jens Isaac's group. And today we have David Wierichs, who's an invited speaker who will tell us about their new paper on the scaling of backpropagation in quantum machine learning, which is a very timely topic, and we're very excited. David is currently a research staff member in Xanadu. Formerly, he did his PhD in Cologne. And I met him because we did a quantum hackathon once together, very successfully. And then we were interns in Xanadu at the same time, hence the merge. I'm really supportive of all of this. So, David, you can take it away. The idea is that we have roughly 30 minutes with hard cut out at 90 minutes. So, like at 12:30.
Uh-huh.
And how would you like us to deal with questions?
So I don't know, in Google Meet, I kind of can't see you, but you can just use this raise hand option, I would say, and then this kind of interrupts me naturally. Maybe we can do it that way.
Okay, then you self-moderate questions.
Sure. We're not that big of a crowd, I guess.
Good. Then awesome. Take it away.
Yeah, thanks a lot, Elias, and thanks a lot for the invitation to talk about this project we recently finished on backpropagation scaling in parametrized quantum circuits. And this is work by Joseph Bowles, Jae-Young Park, and myself. And yeah, Joseph also is present, as you probably have seen. So yeah, we can answer questions with full force. And we're all working at Xanadu. And yeah, let's dive into the project. So backpropagation, what is that again? With the example of a neural network, it basically means that we have some cost function that depends on some parameters that somehow, somewhere, for example, sit in a neural network, and we want to compute the gradient. And backpropagation does this by kind of going through the computational graph in reverse and applying the chain rule automatically. And the crucial feature is that the gradient of this cost function can be computed at about the same cost as the cost function itself. And then there might be some constant overhead, but essentially it's the same cost. And this basically made modern machine learning possible or scalable, if you will. I'm going to give like a small numerical example for this later on, which really shows that there's like, without backpropagation scaling, whether it be with backpropagation or some alternative method that scales similarly, there wouldn't be large language models or something like that. So the second part of the title is parametrized quantum circuits. So we should talk about what we mean by that. We consider parametrized quantum circuits where we have some encoding or state preparation layer V that might take any shape or form, and then some exponentially generated gates with generators GJ, which are going to be quite important in this work. And we apply these gates sequentially after applying the state preparation circuit, and then we measure some observable H, which is also going to be quite important, in particular in its relation to these gate generators. And we can measure the cost function C of theta, which is just this expectation value, as usual, to a precision epsilon with 1/epsilon² shots. Now, if we want to compute gradients of these parametrized quantum circuits, for example, to train them, as we would for classical machine learning, then we probably want to compute, then we can use a number of methods to compute this gradient. Actually, there's a lot of methods. For example, we can use finite differences, which is the standard technique from classical computing, I would say. There's a parameter shift rule, which uses Fourier analysis of the cost function and uses this unitary nature of quantum gates to do something very smart about differentiation. There's a generalization of these shift rules. There's a stochastic version. There's effective generator parameter shift rule. There's something like a stochastic pulse parameter shift rule. There's a pulse generator parameter shift rule. There's proper parameter shift rules. There's linear combination of unitaries, generalized circuit differentiation through spectral decomposition, and circuit differentiation through generator decomposition. So let's just say there's quite a lot. And all of those scale linearly with a number of parameters. And what do we mean by this? It means that if we want to compute the gradient to L infinity norm precision epsilon, then we need a number of shots that scales linearly in the number of parameters lowercase n, and still with 1/epsilon², as it is the case for standard expectation values. And more precisely, we can say that the time times memory requirements that we need for the gradient has at least a linear overhead over the time times memory requirement for the cost function itself. And this definition or this behavior is exactly what this project is all about. So we have at least a linear overhead. To give an example, consider a circuit where we have n Pauli rotation gates. So all of these exponential generators, Gj, are just some Pauli word. Then we can use the parameter shift rule. And for one specific parameter, we can compute the partial derivative using two shifted evaluations of the original circuit. So we don't need additional memory per se, but we need two circuits to compute a single derivative entry. So for the full gradient, we need two n circuits. We can choose to evaluate those circuits or execute them in sequence, or we can do it in parallel. But either way, this product of time times memory overheads is going to be at least linear. And in this case, it's going to be 2n. And the second example is the linear combination of unitaries method, or a generalized Hadamard test, if you will, where we use an auxiliary qubit. So we increase the memory slightly, and we also need additional gates, namely this controlled insertion of the generator Gj at the right position during the circuit, and then a slightly modified measurement. Here we only get n circuits instead of two n circuits, but they are slightly larger than the original circuits. So what exactly is the problem here? We have linear scaling, and that sounds fine. No, I mean, for complexity theorists, maybe it's like a very nice scaling. It's even the nicest of the polynomials. So what exactly is the fuss about? Like, why do we have a problem with linear scaling? To give an example, for quantum machine learning, if we have a model with 10,000 parameters and 1,000 data points that we want to train on, and we assume that we can execute a circuit in 1 microsecond, which is quite optimistic given that on, I think, superconducting hardware, we need 100 nanoseconds for a single C0 gate. So there's a very optimistic rate at which we could execute circuits. Then we will require half a year to measure a single gradient to precision 10 to the minus 3. And that's obviously too long. For NISQ applications like a VQE, measuring the water molecule to a chemical accuracy takes more than 2 days, and measuring the gradient of some hardware-efficient ansatz with a single layer, which would correspond to 208 parameters, would take more than 2.5 years. So we basically haven't started training yet. We just evaluated a single gradient, and 2.5 years passed. That's clearly unfeasible. So instead, what we want is backpropagation scaling. In the classical context, as I mentioned, it basically means we have a constant overhead in the number of parameters for computing the gradient compared to computing the function itself. We're going to relax this a little bit and use at most logarithmic overhead, following a recent definition that you might be aware of in the literature. And yeah, this basically means we have this multiplicative factor CT and CM for the time and memory requirements that we require both to be at most logarithmic in the number of parameters. It's going to be quite important that we refer to the number of parameters all the time, because for quantum circuits, there certainly are other quantities that are considered for scaling usually. And sometimes we will need to make some assumptions in order to make kind of useful statements. You will see that we will go through some scenarios to make those statements more meaningful. So to just not be too pessimistic about quantum, actually modern machine learning in the classical domain also would be unfeasible without backpropagation. So if we consider GPT-3, which has about 10 to the 11 parameters, the speed up of going from a linear overhead to a constant or logarithmic overhead, which is about the same in this case, is a speed up of 10 orders of magnitude, meaning that we simply wouldn't have GPT-3 without backpropagation. I think that's fair to say. And what's more is that we have a statement, as you might be aware, that there's no backpropagation scaling for parametrized quantum circuits in full generality. So if we say, is there a method that can, for any parametrized quantum circuits, achieve backpropagation scaling, then the answer is provably no. So what do we do to kind of circumvent this statement is we do something a bit more specific than doing all parameterized quantum circuits you could do. And the circuits we look at are commuting generator circuits. And now, well, you might guess what those circuits are. They are circuits with commuting generators. So far, so good. And for this, we have a theorem which states that if we have an n-qubit circuit of this structure I introduced before, where we apply parametrized unitary after some encoding unitary V. And we furthermore assume that all the generators commute and that the generators commute or anti-commute with a measurement observable H. And that is, we can decide for each generator whether it commutes or anti-commutes. They don't have to agree on this. Then we can compute the gradients without bias and to precision epsilon using 1/epsilon² shots with a single n-qubit circuit. And what this means is basically that we don't have a memory overhead anymore. The memory overhead is 1. We haven't talked about the depth of this circuit, though, so that's going to be important. Before we turn to this more specifically, let's see how this theorem works. It's actually quite a simple proof. So why does this work? We can consider a single partial derivative and see that this is just the expectation value of some observable I times the commutator of G, J, and H, which we call OJ. And what we have used here already is the commutativity of the generators. So usually the generator for this derivative would be stuck somewhere in the middle of the variational circuit. But because the generators commute, we can kind of pull it to the measurement observable. And this OJ is either 0 if GJ commutes with H, or it's non-zero if they anti-commute, but then it has the specific form 2I times GJH. And then we can compute the commutator of 2 such observables. So of the 2 observables we would need to measure to obtain 2 different gradient entries, and they commute. This is obvious if OJ or OK is 0 already, but even if they're both non-zero, they still commute. And this means we can measure them.
Sorry, David, mini question. I'm a bit confused. So this is saying that if GJ anti-commute, so if GJ, so if the generator for theta J commutes with the measurement Hamiltonian, then the gradient is 0.
Yes. And that's
Isn't
because
that bad?
Well, so the reason we relaxed it to this statement, so the first version we had for this statement is that we would assume anti-commutativity exactly for this reason, because if they commute, indeed, you can kind of pull through the generator to the measurement. You can pull through the gate, and then it just kind of annihilates with itself by commuting through the measurement observable. Mm-hmm. However, this remains interesting if you want to fix a circuit and maybe have multiple observables, or you want to have an observable that consists of a sum, and then this makes sense. But very good question. Yeah.
Thank you.
Sure. So these commute. So we can measure these observables simultaneously. And the way this looks is we execute the original circuit, and then before measuring H, we instead execute some diagonalizing unitary D, measure in the computational basis, and construct the gradient from these measurements in post-processing. So as I mentioned before, the memory overhead is just none. So we have a multiplicative factor of 1. And but we need this additional unitary D. And because we don't know the relation of the depth of D to the depth of the original circuit, we basically don't have a guarantee for backpropagation scaling yet. So there's additional features these commuting generator circuits come with. The first is that if we fix an order of derivatives, we get all the derivatives simultaneously. So this trick we just pulled off for the gradient works for any other order of derivatives as well. And what's even more crazy is that you can do it for all odd order derivatives or all even order derivatives at once. So you basically just need to execute 2 different circuits, and then you get all the derivatives, which might seem a bit like a free lunch statement, but it's important to keep in mind that the precision becomes worse and worse with the order of the derivative, namely exponentially with the order. So it's we get a very bad approximation of high order derivatives from this. And it's important to keep in mind that the diagonalization unitary D might become quite involved if we want to measure that many observables simultaneously. Another nice feature is that the quantum Fisher information becomes constant for these circuits. For this, we don't even need this requirement about the Hamiltonian. We just need the commutativity of the generators, because the quantum Fisher information in general doesn't depend on the measurement observable. And basically, it just becomes the covariance matrix of the different generators in this prepared state using the encoding unitary V. So in the scenario of QML, where we would encode some data points using V, we would have to measure the Fisher information once per data point, but we wouldn't have to measure it again while training the parameters, because it's constant for given a fixed v. And that's quite nice. So we can, for example, run quantum natural gradient at much lower cost. And overall, we can say these high order derivatives, they can be used for quite advanced optimization schemes, but typically that's not done because it's too expensive. And for these circuits, stuff becomes actually feasible. So at least some approximate versions of Newton's method or something like this might be possible using these commuting generator circuits. So now these circuits might seem a bit like a gift that keeps on giving and is like very nice and so much is possible. So maybe we should be careful not to do something trivial accidentally. Like maybe these circuits are so nice because they can't achieve much or something like that. So the question is fair to ask, are these commuting generator circuits still powerful? And it turns out that they are. So on one side, we can make the circuit itself, and computing this expectation value C of theta, we can make that hard just by implementing a hard encoding unitary V that's classically not easily doable. But even if we choose to pick a very simple V, let's say even the identity, then we still have IQP circuits, so instantaneous quantum polynomial circuits in the class of circuits we're considering here. And for those, it is known that sampling is hard classically. So one scenario one could envision is training such a circuit, maybe even using classical methods, because this expectation value is not necessarily hard to compute, but then using a trained circuit to sample from it. So that might be a nice application where one really plays with which tasks exactly are hard and which are not classically. And then another important question is whether we actually can train parametrized commuting generator parametrized quantum circuits once we computed those gradients. So in other words, do these circuits have barren plateaus or not? And there's a conjecture regarding the dynamical Lie algebra of a quantum ansatz, or quantum circuit ansatz, which says that the dimension of this algebra basically captures how the gradient vanishes, or the gradient magnitude. And for our circuits, for these commuting generator circuits, because all the generators commute, they cannot give rise to new elements of the algebra. So every element of the algebra that is in the dynamical Lie algebra, we need to put in explicitly by inserting a gate for that. And this means that the dimension of the dynamical Lie algebra is basically the number of parameters, and that's bounded by the number of qubits times the depth of the original circuit. And in other words, we can say, as long as we don't use exponentially many parameters, we're good to go, and we won't have exponentially vanishing gradients as long as this conjecture holds. Of course, usually we wouldn't use exponentially many parameters because then kind of the whole scaling question is kind of redundant anyways. So now let's be a bit more specific about these circuits and restrict to Pauli words as measurement observables and generators. This is not too uncommon because many gates are generated by Pauli words, and many observables we might want to measure actually are decomposed into Pauli words anyways in practice in order to get a nice measurement scheme that is feasible on a quantum computer. So this automatically guarantees that H and the generators GJ commute or anti-commute. That's kind of nice. We just need to take care of the generators commuting with each other. And the second very nice feature of this subclass of commuting generator circuits is that the depth of this diagonalizing unitary actually is bounded in this case. And this leads us to the relative additive overhead. So I subtracted the 1 to get kind of a nicer scaling quantity. The additive overhead becomes n over log n, where capital N is the number of qubits, divided by the depth of the original circuit. And this is now one of these points that I kind of teased earlier, where we want to make a statement about the scaling in the number of parameters, lowercase n, but we have a statement in 2 different quantities. So in order to make stuff a bit more concrete, we might want to play through some scenarios. And for this, there are some circuits with different depth, so logarithmics, square root, or linear depth in the number of qubits, and either with a single layer of parameters, or we could also reuse parameters between generators, or in the second scenario, parameterizing all the gates in the circuit. And then we can look at this additive overhead, and we see that basically Logarithmic scaling is only guaranteed if the original circuit already was of linear depth. In these other cases, this additive overhead actually is polynomial or some square root behavior divided by some logarithm. So we don't have a guaranteed backpropagation scaling for sublinear depth. However, that's just a bound, that's just a guarantee. So we will see that this doesn't necessarily exclude that we have cases where we do get backpropagation scaling, just not provably so maybe, or not in general. So let's be even more specific and turn to the X generator ansatz, which now fixes the generators to be tensor products of Pauli X and operators and the identity. And the measurement observable is fixed to be some tensor product of Pauli Z and identities. And in this case, we have this explicit construction for the diagonalizing unitary, which applies a number of 2-qubit control Z operations. And the number of these, the depth of this circuit is basically equal to the support of the measurement observable. So just the number of Pauli Zs we put into H. Now, again, we have a quantity that doesn't relate to any of the other quantities. So not to the number of qubits in total, not to the depth of the original circuit, and not to the number of parameters. So we can write down this bound on the size of the measurement observable, for which we do get backpropagation scaling as a guarantee. We could also be a bit more practical about this and just say, if we have a single Pauli Z operator as our measurement observable, then we get a depth of 1. And then we have backpropagation scaling even in the classical sense. So our overhead factors are both basically 1. And this is also the setting we're going to use for numerics. So in the numerical example we did in the project, we look at a classification problem of bars and dots that look like the following. So we have either consecutive values of plus or minus 1 in some data vector, or we have alternating values of plus or minus 1, and then we add some Gaussian noise. And the length of these data points we used is 16. This is also the number of qubits we require for our models. And the task is then to just classify these data vectors to be either bars or dots. And one crucial feature here is that this classification does not depend on how the bars and dots are arranged. So if we translate the vector, then this shouldn't change the classification because bars remain bars and dots remain dots. The encoding we use, this layer V, is very simple in this case. So we use just Pauli Y rotation gates, 1 for each entry of the data vector. And this way we load the classical data into the a separable state. And then we apply 3 different models. The first is an X generator circuit, the one I just presented, with a translation equivariant set of generators. So to kind of accommodate for this redundancy in the input data, or the symmetry in the input data, we want to make the circuit translation equivariant, which means that the prediction of the circuit is going to be invariant under these translations, which is exactly what we want for invariant data. The second model is again translation equivariant, sorry, but it uses non-commuting generators. And here we use the parameter shift rule to compute the gradients, whereas in the first model we can use our parallelized tactic. And for both these models, we use the measurement observable, where we sum over the Pauli Z operators on each of the qubits, which again is a translation equivariant measurement observable required for this invariance. The last model we consider is the quantum convolutional neural network with a single Pauli Z operator on the last qubit, and again using the parameter shift rule for the gradient. And all this is implemented using Penny Lane in an open source repository that I'll share at the end. Cool, so here's a brief depiction of these models. The first one is just the X generators, as we introduced earlier, with up to 3-body interaction. And this plus sim always means that we add all the symmetrized versions under translation. And then model B looks quite similar, except for it has 4 blocks, where each block is started by a Pauli Z and Pauli Y single qubit rotation layer. And then we only have up to 2-body interactions of the Pauli X gates. And the quantum convolutional neural network is adapted from the literature and alternates between a convolution and a pooling layer kind of has this binary tree-like structure. Numerically, or in numbers, our models have similar amounts of parameters, n. The number of generators that are used are quite different between the models A and B and the model C. And the number of circuits we require for single gradient evaluation also differs, but in very different ways. So for the first model, we need n circuits, because the theorem stated that we need one circuit for a Hamiltonian that commutes or anti-commutes with all the generators. But here we have now a sum of Pauli operators, and this is exactly the scenario that Elias' question pointed at, where now we kind of decompose the circuit according to the sum of the Hamiltonian. We treat them as n different circuits that each require one circuit for the gradient evaluation. The second model requires a quadratic number in the number of qubits and a linear number in the number of blocks that the circuit uses. And the last one, again, is linear because of this tree-like structure. So it doesn't use as many gates, but it has a large prefactor, which in practice for our 16-qubit example leads to these numbers of circuits per gradient: 16, 1006, and 860. So this leads to the following results. We run 50 optimization iterations for 10 trials for each of these three models. And we see that the commuting generator circuit seems to be doing quite well. But more interestingly, let's look at the classification accuracy of some test set. And here we see on the x-axis the total number of shots used for these 50 epochs of training. And on the y-axis, we see the test accuracy. And as we can see, the non-commuting and the commuting circuit, so these equivariant circuits that use either commuting or non-commuting generators, they do somewhat equally well after 50 epochs, but the commuting generator circuit uses much fewer shots to achieve the same accuracy. And the quantum convolutional neural network still is kind of in the training phase and would require some more resources to converge, which might also be due to the reduced number of generators that it uses. So we don't want to make the case that commuting generator circuits are per se super powerful or like a particularly powerful class, but we want to highlight that we significantly reduce the cost while not deprecating the performance, at least for this example. So one always has to be careful with benchmarks, but this is kind of the reasonable example we looked at, and we found that the performance is not deprecated here. So it seems like the circuits are still good for something while reducing the cost significantly. Now, one could say that all this construction is a bit specific, maybe. So these commuting generators might be too restrictive, and in some applications, we might have other constraints to construct the circuit that are not allowing us to follow this template. So instead, we can consider commuting block circuits. We can have a theorem for this. And here, the essential new stuff is basically written in black, and the other part I grayed out a bit because it's basically just the other theorem with a slight extension. So we now consider an n-qubit circuit with B blocks, where blocks are defined such that within each block, the generators commute. And between blocks, there's a fixed relation of whether the generators commute or anti-commute. So oppositely to how we worked with the measurement observable earlier, we cannot pick per generator, but we have to fix the relation between the blocks. And yeah, given such a circuit, where again, each generator also commutes or anti-commutes with H, we find that we can compute the gradient with 1 over epsilon squared shots of 2b minus 1 circuits. So we really need 2b minus 1 over epsilon squared shots. And each of these circuits has n plus 1 qubits. So we need an auxiliary qubit. And the construction looks like this. On the left-hand side, we have the original circuit with this block structure. And on the right-hand side, we repeat the blocks up to those where we want to take the derivative. And then we need to apply some controlled version of the remaining circuit and of a mild variation of the remaining circuit. So this leads to increased depth. And we also need to run 2 of these circuits for each block because of the commuting and anti-commuting property of the Hamiltonian with these generators. So there's some details there, but for each block we need 2 circuits except for the last one, which gives us this number 2b minus 1. And then there's also still a diagonalizing unitary d. And as special cases, we can go back to b equals 1, which gives us back the commuting generator circuits, where we don't need the auxiliary qubit, of course, and we only get one circuit for the gradient. Or we can do the opposite and say each gate is its own block. And if we, for example, consider the case where each gate is generated by some Pauli word, then the requirements of the theorem are satisfied, and we can basically get back this linear combination of unitaries or Hadamard test construction that I showed earlier. So we basically have a method that interpolates between the extreme cases of having to do a linear number of circuits or a constant number of circuits. And generically for this construction, we know that the overheads in the time requirements is going to be 2 or larger, just for the most general case, just because of these additional gates we have to execute and the diagonalizing unitary. And now, coming to the end, there's some other applications of this perspective that we provide in this project, which is if we consider algorithms that grow circuit ansatz while optimizing them. For example, ADAPT VQE or rotor select are such algorithms. Then we need to evaluate newly added gates. So these algorithms decide which gates to grow onto the ansatz by measuring their gradient at 0, for example. And this can be done in parallel with our method, which also was observed very recently in the literature. And then we can greedily train these newly added blocks because we can consider all the other gates that already are in the circuit to be part of the encoding unitary V. And then we can train these newly added gates, which typically come in layers, so that they commute automatically. So as I already indicated, many circuits can be seen as commuting block circuits. I gave this extreme case where each single gate would form a block, but we think that there might be special cases where we can train existing circuits faster than with the parameter shift method, maybe not with backpropagation scaling, but something in between. And with this, I would like to conclude. So about backpropagation scaling in parameterized quantum circuits, we can say that in general, this is excluded, as was recently shown in the literature. It's guaranteed for some specific circuit classes. It's achievable in practice for even more circuit classes. And it's going to be an important feature, we're convinced of that, for both quantum machine learning and NISQ use cases in the future. And maybe to zoom out a bit in the very last point, we want to stress with this project that it's going to be important to use tailored parameterized quantum circuits for applications, tailored to the training methods we want to use, tailored to the use cases. And we want to move away from just using generic Ansätze and just see what happens and hoping for the best with whatever ansatz. So yeah, this is a point we really want to stress here. And yeah, we hope that this maybe will find some friends as a direction of further research. So with this, I would like to thank you for your attention. Here's the link for the GitHub repository for the numerics and the paper link. And yeah, if you have any questions, I'm happy to answer.
We had an accidental raise hand. Man, very nice.
Thanks.
I have one. Ooh. How do you do that? Okay. I have a question. I think you might have said it, but I don't remember. And earlier when you said that for this backpropagation, you can measure some other circuits and then get the gradients from post-processing the measurements. Do you have guarantees that this post-processing, like the length in time of the post-processing, will not become exponential or something?
So the way this works is that the diagonalizing unitary, D, there's basically two questions about that part, which is, can we find it efficiently and implement it efficiently? And these Pauli commuting generator circuits, we know that both is true. So finding it is efficient, and the length is this n over log n depth. So it's like a small polynomial in number of qubits. So that's fine. And the post-processing then should just be kind of matching the combination of computational base states or of like Pauli Z operators to the right operators that you actually wanted to measure. But this kind of, you need to have this because finding the diagonalizing unitary also means that you know what you map to, right? You kind of have to, otherwise you're just implementing some unitary. So yeah, the post-processing itself should be fine, yeah.
Thanks. Does anyone else have a question? Reminder that Joseph Bowles is also in the call, so we can have full force response to your questions.
One thing that I wondered was, so you said that the Lie algebra has the dimension of the number of parameters essentially, or parameters times depth. Like essentially it's linear or quadratic depending on how you count. How does this compare with like does this mean that there is like a lot of symmetry in your circuit? And add-on question, if answer yes, then in how far would this mean that one could write the circuits in some more clever way using the irreps of the symmetry to make things like more like to bring it closer to actual classical simulability?
Yeah, I think that's a nice question. So maybe to like detour briefly and then answer your question.
Sure.
So when I remember, like in my PhD, I personally like was confronted with IQP circuits for some time, and then I was very confused by them being hard because they commute, like all the gates kind of have a common eigenbasis, so you do like diagonal stuff, and everything seems kind of like it should be easy, but it's not. So sampling from these circuits, for example, is not easy. So yeah, I think you're right. So if one was to try to simulate them classically, then doing such a thing like kind of going to a nice irreducible representation and kind of using the symmetry to, I guess, basically convert everything that's a matrix to like some diagonal matrix and therefore to a vector, basically makes sense. So I think like the intuition is quite right. And for some tasks like computing expectation values, this might give you a simulation tool if the encoding unitary V is not too hard, for example. So if you want to compute just expectation values and you have a simple V, as we did, for example, in our numerics, then you can definitely simulate this classically, as far as I'm aware. So yeah, I'm not sure about like symmetry, I guess.
So I can see V sort of as a resource in the sense that, well, the circuit itself, if I apply to some nice state, then everything is nice, or some nice ensemble of states if I have like function encoding and encoding. But like if I have some, say, sufficiently high random state, then quite likely the state is just in a basis where whatever I did before doesn't help me at all.
Yeah, I mean, yeah, exactly. I mean, you can make a quantum circuit, like a variational quantum circuit, hard by including a single unitary that's hard, right? So it's a bit of like a weird procedure maybe, but yeah, one scenario where these circuits are clearly not simulable is if the part that you do before you even throw parameters into the game is implemented already in like something that's hard. So yeah.
I think lately Jens was also saying something like that if you have an MPS and then you apply like essentially an IQP circuit, and he can contract this efficiently or something like this. So
yeah, that sounds like that does sound like computing like an expectation value, right? If you do the contraction, like you have an MPS, which probably captures like all most easy, classically easy circuits. And then you can do whatever in like parametrized fashion afterwards, and expectation values remain tractable. That makes sense, I think.
And I mean, the problem you were looking at is computing expectation values, right?
Yes, in this particular example, the reason we sorry.
No, so yeah, go on. Sorry.
So yeah, these numerics basically show that these circuits remain expressive and that we can train them somewhat cheaply. And I mean, there's examples like generative models or stuff like this where you really want to sample from the quantum state, and even if the training might be tractable, or like evaluating the cost function of the training step might be tractable, you still need the quantum circuit in the end.
Yeah, that's true. Though, I mean, in that case, it might be like in terms of efficiency, the best thing to train it classically and then just realize the guy in the lab if you need to sample from it.
Yeah, then you get backpropagation scaling by backpropagation.
Exactly.
Indeed. Yeah, I mean, it depends a lot, I guess, on the specific scenarios you like, what you want to do and how you want to train.
Yeah. Yeah. Yeah, Elias, you go.
Sorry, just to throw in an easy one in between. What about re-uploading? What if you put fixed gates in between your blocks which don't commute nor anti-commute with the observable? So like everything you have, the same way you have it, just I come in and put some unitary in between. And you don't need to take gradients with respect to this, but I just put it there. Then
so you say they neither commute or anti-commute with the observable, but do they have like a fixed commutation or anti-commutation relation with the generators of the gates?
I mean, I think for all intents and purposes, they're fake.
I think they probably have. Probably it's just an X encoding. Then
yes,
probably
I
just
could imagine.
Commute with your polystrings.
I mean,
or anti-commute.
The tricky part with like identifying these blocks with layers is that one quickly forgets that if I have just like some Pauli layers of single qubit rotations, there's not such a fixed relation, right? Because the Pauli Y and Pauli X on the same wire will anti-commute, but Pauli X and Pauli Y on different layers will commute. So it's like a bit like unintuitive how to map these between layerized Ansätze and these blocks. But I mean, you probably can do like this commuting block strategy for this scenario of having data re-uploading. I'm not entirely sure like how that scales, like whether there's a particular construction you could do to make these blocks kind of not blow up linearly.
So you're saying
I'm not sure.
So if I wanted to use this strategy with re-uploading, I could try to think of ways not to break it. But if I wanted to break it, I could break it.
Yeah, pretty sure. The way we build things, I'm pretty sure you could break it.
Okay.
Because I mean, a lot of these steps hinge on being able to pull the generators through to the observable. So
yeah,
yeah,
I mean, it makes sense to me.
Yeah. It also seems like a bit of a strong statement to just maintain scaling while doing like more fancy stuff. Like at some point you have a general circuit, and then we know this statement can't be true. So
yep, cool. Thanks.
You said that you tested expressivity. How did you measure that, or how did you?
Oh, I just meant in the sense that we ran like this simple benchmark and it still works. It actually like worked pretty well, right? Like if we look at the classification accuracy, it actually performed best of these. I mean, one could like throw a lot of measures around like the depth of the original circuit, whether that matches the localness of the generators we use. Like there's all sorts of things one could argue about, but this benchmark was mostly to show that these circuits still can do something that other circuits are used for, and they are just drastically cheaper. I mean, this is 2 orders of magnitude fewer shots. So
I have to say I really appreciate this graph, because like it's not the one you usually see. You usually would see number of epochs, and what this is saying is that if you're counting the number of shots, the first one has finished training before the second one has done, like before the other two have done one step.
Exactly. So it's like, in like this standard like epoch counting, our graph would be very boring.
I mean, you would expect
the blue one
to take the same number of epochs roughly, right?
I mean, we fixed the number of epochs, so we didn't run like until some conversions or anything.
Sure.
So it would just be, I mean, like slightly differing numbers of. I mean, if we really just count epochs, it would be like the blue and the black lines would be very similar, I would say.
Okay. And then, so this is a bit of a deviating question, but I'm a bit confused that the QCNN takes longer, because your problem has, like, the local correlations are very important. Like, like for the QCNN to classify, it just needs to measure like two sets of 3 dots contiguous, and if they are the same color, it's one class. If they are alternating colors, it's the other class. Just I'm a bit confused that the QCNN wasn't just much better at this.
Well, what was actually the test data, the loading data?
It's 1 second.
It's worth saying that there's noise, right? So it's not
Right.
just you can measure 3 and classify.
Yep. Okay. Fair point.
Yeah. So if you look at like these 3 here and these 3 here or something like that, I mean, yeah. Like,
well, but the QCNN kind of looks at all pairs of 3 in a way.
I must admit, I'm not really really an expert on that part. I don't know, Joseph, whether you have some more insight on that.
No, but this was just, I'm like,
much.
yeah, I'm zoomed out curious. I'm not really asking hard questions.
Yeah, I don't have any strong intuition why the QCNN didn't perform as well as it did. I sort of feel like equivariant architectures are just the better way to go for these types of problems. They seem more sort of systematically thought out, which is why they're doing better.
Yeah, makes sense. Thank you.
I mean, really, it's also like we didn't go for like a proper benchmark here, right? Like we didn't do a hyperparameter optimization in like an exhaustive way or anything. So it's like that was not the goal of the numerical experiment.
Sorry, you didn't see it, but I gave you a thumbs up with my thumb.
Thanks.
Any more questions, Alex?
Yeah, I've one more very open question. How does a paper compare with like this other quantum backpropagation paper from a few weeks earlier?
Yeah, so
I see it's completely different techniques, but like still, I guess there are multiple ways to answer that question, and I invite you to answer in all the ways.
Yeah, so I mean, I think this is like very well aligning with what we want to like message with this paper on the broader level, which is that yes, we can prove rather general level stuff, like statements about all the parametrized quantum circuits, for example, but maybe those circuits are just not the ones we should be caring about that much. I mean, it's valuable statements and it's very nice to have those for sure, but maybe we shouldn't be super surprised if we do arbitrary stuff that we don't get specific performance. You know, it's like somehow it makes sense to have to put in work and like choose specific things to solve a specific problem, because otherwise we're building an unbiased structure somehow regarding the problem you try to solve, and then we expect it to just solve all the problems, right? Because we didn't bias the thing. So it's kind of weird to just expect this to work, in my opinion. And I don't know if like people that know me might know that I have a somewhat similar feeling about the barren plateau concept, where basically you say if you do random stuff, you don't get specific gradient directions. Like you just flat out like end up anywhere in some like random state. So you can't train that well. Which again is a statement about kind of the full generality of quantum states, but maybe we just don't want to consider all the quantum states. I mean, Hilbert space really is a bit too large to consider all of the states. So doing specific things is really, really important, I think, and fixing specific models that have very nice properties either for the application or in terms of the methods we want to use. And then also, for example, initialization methods. I don't really see a reason to initialize a parametrized quantum circuit fully at random if you want to scale it up. You just end up somewhere. I mean, it feels, to me personally, it feels a bit like you're kind of preparing a nice initial state and then you do something, you end up somewhere and then you start training from this random point. So yeah, but that's of course very much in the like opinion space.
I guess we're quite aligned there.
Sorry?
I guess we are quite aligned in that opinion.
That's fair. That's good to hear. Yeah. So yeah, this, I mean, yeah. So, and to maybe like come back to the question more in particular, the reason why this theorem from the recent paper on backpropagation scaling not being possible without having multiple copies of a quantum state is that we do not claim that it's possible for all the parametrized quantum circuits, but just for the specific ones we assume. Yeah. So that's how they relate.
But I mean, at the same time, they also had like their own, say, suggestion for quantum backpropagation algorithm.
Yeah.
Which then has different scalings, different properties, and complete different technique.
Yeah.
Like, how would you like say when is which better to choose?
I think I would defer that question to Joseph.
I'm not sure if I'll be much more use. I mean, that paper appeared on the archive while we were writing this one, so we didn't really have much time to go through it. So I'm not familiar with the details. I know they do something with shadows to approximate the state, but I can't comment more than that without thinking a bit more.
All right.
But just to be sure, it is safe to say that having commuting generator circuits is not necessary for backpropagation scaling, yeah?
Not that we know of.
I mean, like a counterexample would be to use these commuting blocks with a constant number of blocks, right? If you scale up your circuit and you put more and more parameters, you might still have the same number of blocks. For example, if you just take a fixed architecture and you increase the number of qubits, I don't know why one would want to do that, but you could do that, and then the number of parameters would increase while the number of blocks might not increase. So then you would get backpropagation scaling. If that makes sense.
But there could also be completely different architectures for which you can do this that we don't know about. So.
Yeah, yeah.
Good. Can I ask you another difficult question on the opinion space? So I'm on your boat. We should use tailored architectures for tailored problems. But now, can you give me an example? Like, what is a problem for which you have an idea of what would, like, what architecture you would use to solve the problem, and like a real problem?
I mean, so there's like maybe one thing we encountered here already is to use equivariant circuits to get symmetry invariant classification, which is, I mean, I guess it's a bit trendy, but that's certainly a good idea if you don't want to overparameterize vastly and then have to compute very expensive gradients. And then using this parallelized gradient technique, this backpropagation scaling gradients clearly is an advantage in training, just in that it reduces your cost. So the question kind of is, can you build a model that solves your problem that also has this nice feature of training faster? Or, I mean, this equivariance is, can you build a model that is equivariant while still being, say, realizable on your NISC device or something? Likewise, in, I don't know, a VQE problem, you will tailor your circuit to maintain certain symmetries of a molecule or stuff like that. So I think there's a few examples, and I think there should be more examples of really using structure of your problem to structure the quantum circuit. Because otherwise, yeah, as I said, I think you're just hoping to do the golden solution with like trying everything. So, yeah.
Yep. Do you have a favorite one of those examples?
I mean, I did work on like these VQE symmetric circuits a bit, and that was kind of interesting, and it's kind of nice. The downside to that is that you have to know a bit of quantum chemistry. And that stuff becomes very hard very quickly because many of these classical co-processing steps also actually are not that easy.
Mm-hmm.
I do like this symmetry aspects as well, though. It's yeah.
Me too.
So yeah.
Awesome. Any more questions? I think this was really nice. Good. It seems then that we stop it here.
Cool.
It was as I said. Very nice. Thank you so much
Thanks a lot
for
for having me.
telling us about
Mhm.
this. Yeah. Yeah. It was very nice. I think everyone's
Cool,
free
yeah.
now.
See you
Yeah.
around.
So for reference, like I did the recording. I have no idea how this will be stored. I will cut out the discussion part of the recording. I'll show it to you, and then you can see if we want to make it public or not.
Sounds good.
All right. Then have a
Thanks a
nice
lot.
day, weekend, and August, everyone.
Bye bye.
Bye-bye.
Bye-bye.